Hey there. Today, I'm diving into some groundbreaking research that's transforming industrial waste into a sustainable material for nuclear safety and radiation shielding. What if we could solve two environmental problems while improving the safety of nuclear facilities? Let's explore. First off, let's talk about the problem. Industrial and nuclear waste are major environmental challenges. Every year, millions of tons of polyvinyl chloride, PVC, and asphaltene, a byproduct of oil refining, are discarded. Meanwhile, radioactive waste from nuclear applications needs safe and cost-effective stabilization. But what if we could combine these problems into one sustainable solution? Here's where the innovation comes in. A team of researchers found that mixing PVC or asphaltene with Portland cement creates a high-performance shielding material. The result? Enhanced mechanical properties and superior radiation protection. With 50% PVC, the compressive strength of the cement reaches 4.5 megapascals. And with 50% asphaltene, it doubles to 8.8 megapascals, exceeding nuclear safety standards. Plus, this material removes up to 304% more fast neutrons than regular cement, making it ideal for nuclear waste storage and radiation shielding. This research isn't just a scientific breakthrough, it's also economically impactful. For Egypt, it reduces plastic and petroleum waste, supports nuclear energy safety, and creates new jobs in sustainable construction and waste management. Globally, it provides a cost-effective solution for radioactive waste storage and helps nuclear industries use eco-friendly materials. It even lowers reliance on imported shielding materials. The future of sustainable nuclear safety looks bright. By repurposing waste, we can build a safer future for nuclear energy and environmental sustainability. So, what do you think about using waste for nuclear safety? Let me know in the comments. Don't forget to like, share, and subscribe for more scientific breakthroughs. Hey there, science enthusiasts! Today, I've got an incredible story to share with you about turning waste into a tool for nuclear safety. It's a game changer, and it's all thanks to some brilliant minds working tirelessly behind the scenes. Let's dive in. This breakthrough comes from a remarkable team of researchers in Egypt. First up, we have Professor Dr. Hosam Saleh from the Radioisotope Department at the Nuclear Research Center, part of the Egyptian Atomic Energy Authority in Cairo. Joining him are Emeritus Professor Dr. Ibrahim Bondouk from the Physics Department at the University of Tanta, and Professor Dr. Elsayed Salama from the Basic Science Department at the British University in Egypt. We also have Professor Dr. Hosam Mahmoud from the Radioisotope Department at the Egyptian Atomic Energy Authority, Emeritus Professor Dr. Khalid Omar from the Physics Department at the University of Tanta, and Dr. Heba Essawi, who's with both the British University in Egypt and the American University in Cairo. So, what's the big idea? These researchers have found a way to blend industrial waste, specifically asphaltene and polyvinyl chloride, or PVC, with cement. This innovative mix not only strengthens the cement but also enhances its ability to shield against radiation. Imagine using waste materials to protect us from nuclear hazards. The study, published in Sustainability in 2022, aimed to tackle two significant challenges: managing plastic and petroleum waste and improving radiation shielding. By mixing PVC and asphaltene waste with Portland cement, they've created a material that's stronger and more durable, with improved radiation shielding, especially for neutron absorption in nuclear waste storage. Now, let's talk numbers. Cement mixed with 50% PVC reached a compressive strength of 4.5 megapascals, while cement mixed with 50% asphaltene hit an impressive 8.8 megapascals. That's way above the U.S. Nuclear Regulatory Commission's minimum standard of 3.4 megapascals. And when it comes to radiation protection, the material absorbed 304% more fast neutrons with 50% PVC and 171% more with 50% asphaltene. It's highly effective for nuclear waste stabilization and shielding applications. The benefits of this breakthrough are huge. For Egypt, it means reducing hazardous waste, enhancing nuclear safety, and supporting sustainable construction industries. Globally, this offers a cost-effective alternative for radiation shielding, benefiting nuclear power plants, medical facilities, and hazardous waste storage. This research is just the beginning. Future studies could optimize these composites for various nuclear applications, and industries might scale up production to develop radiation-resistant infrastructure. Plus, this innovation can be applied in fields like medicine, aerospace, and defense, where radiation shielding is crucial. science continues to shape a cleaner, safer world. What do you think about using waste materials for nuclear safety? Let me know in the comments. Don't forget to like, share, and subscribe for more cutting-edge scientific research. The screen displays a subscribe button with previous video recommendations. Hey there, science fans! Today, we're diving into the fascinating world of hazardous waste and a groundbreaking solution from the brilliant minds of Egyptian scientists. It's all about safety and protecting ourselves from harmful radiation. But first, let's talk trash. Hazardous trash, that is. We humans generate a lot of waste. Some of it's just regular garbage, but some is seriously dangerous stuff. We're talking about materials that can be toxic, radioactive, or both. This hazardous waste is a big problem, and dealing with it is crucial for our health and the environment. Now imagine trying to safely store this hazardous waste. You can't just toss it in a landfill. It requires special facilities and robust shielding to prevent harmful radiation from escaping. That's where our story takes us. So, what's the deal with radiation shielding? Well, it's like wearing a super strong sunscreen, but instead of protecting your skin from the sun's rays, it protects us from invisible high-energy radiation. This radiation can come from various sources like nuclear power plants, medical treatments, and even some industrial processes. Shielding is essential to contain this radiation and prevent it from harming living organisms. Think of it as a barrier that absorbs or deflects radiation, keeping us safe. Pretty important, right? Traditional shielding materials often rely on heavy metals like lead, which can be expensive and, ironically, hazardous themselves. Plus, they're not exactly environmentally friendly. That's why scientists are on a quest to find safer, more sustainable alternatives. And guess what? A team of researchers from Egypt might have cracked the code. Let's travel to Egypt, where a team of dedicated scientists has been hard at work tackling this challenge. They've developed an innovative solution for radiation shielding using a surprising ingredient: sustainable cement. That's right, the same stuff we use to build houses and sidewalks can now help protect us from radiation. Their secret weapon? They've figured out a way to enhance the shielding properties of cement by incorporating waste materials like PVC and asphaltene. This is a game changer, folks. Not only does it improve safety, but it also tackles the problem of waste management. This innovative approach has the potential to revolutionize radiation shielding while promoting sustainability. It's a win-win situation. Now let's get down to the nitty-gritty of this scientific breakthrough. The Egyptian team focused on creating a special type of cement composite by incorporating polyvinyl chloride, PVC, and asphaltene, which are byproducts of the petroleum industry. They experimented with different compositions, carefully measuring the proportions of cement, PVC, and asphaltene to find the perfect recipe for optimal shielding. Through rigorous testing and analysis, they were able to evaluate the effectiveness of these composites in blocking gamma radiation. The results were impressive, to say the least. The addition of PVC and asphaltene significantly enhanced the radiation shielding properties of the cement. But that wasn't all. The composite material also exhibited improved strength and durability compared to conventional concrete. Section 5: PVC and asphaltene, an unexpected alliance. You might be wondering why PVC and asphaltene? Well, it turns out these waste materials possess unique properties that make them surprisingly effective for radiation shielding. PVC, commonly found in pipes and flooring, contains chlorine, which is known to absorb gamma radiation. Asphaltene, a heavy component of crude oil, also exhibits radiation attenuation properties. By incorporating these waste products into the cement matrix, the researchers were able to harness their shielding abilities while simultaneously addressing the issue of waste disposal. Talk about a clever solution. This innovative approach not only improves the functionality of the cement, but also reduces the environmental impact associated with traditional shielding materials. It's a prime example of how science can turn waste into a valuable resource. Section 6: Strength and Shielding, the winning combination. The Egyptian team's research yielded remarkable findings. Not only did their cement composites demonstrate enhanced radiation shielding capabilities, but they also exhibited improved mechanical properties. This means the composite material is not only effective at blocking radiation, but also strong and durable enough for construction purposes. They observed a significant increase in compressive strength, which is a measure of a material's resistance to being crushed. This enhanced strength is crucial for ensuring the structural integrity of any shielding structure. The addition of PVC and asphaltene created a more robust and resilient material capable of withstanding the test of time. This durability is essential, especially in harsh environments where shielding structures are often deployed. Section 7. A boon for the environment. Now let's talk about the environmental benefits of this groundbreaking research. Traditional radiation shielding often relies on lead, which is a toxic heavy metal. Mining and processing lead can have detrimental effects on ecosystems and human health. By utilizing waste materials like PVC and asphaltene, the Egyptian team's solution offers a more sustainable alternative. It reduces the demand for lead, minimizing the environmental burden associated with its extraction and disposal. This innovative approach aligns perfectly with the principles of a circular economy, where waste is transformed into valuable resources. It's a shining example of how science can pave the way for a greener and more sustainable future. Section 8. Global impact and future applications. The implications of this research extend far beyond the borders of Egypt. This breakthrough in radiation shielding technology has the potential to revolutionize various industries worldwide. From nuclear power plants to medical facilities and research laboratories, the applications are vast and promising. Imagine hospitals using this sustainable cement to construct radiation therapy rooms, providing safer environments for patients and healthcare workers. Or picture nuclear power plants adopting this technology to enhance the safety and efficiency of their operations. The possibilities are truly exciting. Furthermore, this innovation can play a crucial role in developing countries seeking affordable and sustainable solutions for radiation protection. It's a testament to the power of science to address global challenges and improve lives around the world. Section 9. A sustainable shield for a safer future. In conclusion, the Egyptian team's research on sustainable cement composites for radiation shielding is a remarkable achievement with far-reaching implications. By harnessing the power of waste materials like PVC and asphaltene, they have not only enhanced the effectiveness of radiation shielding, but also paved the way for a more sustainable and environmentally friendly approach. This innovation holds immense promise for various sectors, including healthcare, energy, and research, and has the potential to revolutionize how we protect ourselves from harmful radiation. As we continue to generate hazardous waste, it's imperative that we find innovative solutions like this one to manage it responsibly and ensure the well-being of both people and the planet. So there you have it. A groundbreaking discovery that's changing the game in radiation safety. Thanks to the ingenuity of these brilliant Egyptian scientists. Keep those questions coming and never stop exploring the wonders of science. We produce a lot of waste. Every day, tons of plastic, industrial byproducts, and construction debris end up in landfills. But what if we could transform this trash into something valuable? What if we could turn waste into a resource that protects us from harmful radiation? This is the exciting potential of new technologies using waste materials to create advanced cement composites. These composites, made by combining cement with industrial byproducts, are not just good for the environment, they also have remarkable properties that can shield us from radiation. This innovation offers a promising solution for a safer and more sustainable future. Imagine a world where the materials we once discarded are now essential components of our buildings, protecting us from invisible threats. This vision is becoming a reality thanks to the ingenuity of scientists and engineers who are turning waste into a valuable resource. Portland cement is the most common type of cement. It is a fine powder that, when mixed with water, forms a paste that hardens into concrete. We use concrete everywhere, in buildings, bridges, and roads. PVC, or polyvinyl chloride, is a type of plastic. It is durable, lightweight, and inexpensive. We find it in pipes, flooring, and packaging. Asphaltene is a heavy, sticky substance found in crude oil. It is typically removed during oil refining. Each of these materials plays a crucial role in creating radiation-shielding cement composites. Cement provides the basic binding matrix holding everything together. PVC acts as a filler, increasing the material's volume and influencing its porosity. Asphaltene, with its high density and complex structure, enhances the composite's ability to attenuate gamma rays and shield against neutron radiation. By combining these seemingly disparate materials, researchers have unlocked a synergistic effect. The resulting composite is more than the sum of its parts, exhibiting enhanced properties that make it ideal for radiation shielding applications. Creating these advanced cement composites is a meticulous process. First, researchers carefully select and prepare the raw materials. The PVC is often ground into a fine powder to ensure even distribution within the cement matrix. Asphaltene, being a viscous substance, requires special handling and mixing techniques to achieve homogeneity. Once the materials are ready, they are combined in specific proportions according to the desired properties of the final composite. The mixture is then poured into molds of various shapes and sizes depending on the intended application. After casting, the composites undergo a curing process, typically involving controlled temperature and humidity conditions. This crucial step allows the cement to hydrate and harden, binding all the components together and giving the composite its final strength and structural integrity. Section 4. Strength and Structure, Testing the New Material. To assess the effectiveness of these new composites, rigorous testing is essential. One crucial aspect is evaluating their mechanical strength. This determines how well the material can withstand pressure and stress, which is vital for ensuring its longevity and reliability in various applications. Researchers use specialized equipment to subject the composites to compressive strength tests, measuring how much force they can withstand before fracturing. Another important parameter is porosity. This refers to the presence of small voids or air pockets within the material. Porosity influences the composite's density, permeability, and ultimately, its radiation shielding capabilities. Various techniques such as gas adsorption and mercury intrusion porosimetry are employed to accurately measure the size, distribution, and volume of pores within the composite. These tests provide valuable insights into the relationship between the composition of the composite, its microstructure, and its macroscopic properties. This knowledge allows for further optimization of the material, tailoring its characteristics for specific radiation shielding requirements. Section 5. Shielding the Future Applications in Radiation Protection. These advanced cement composites born from the transformation of waste hold immense promise for a safer and more sustainable future. Their ability to effectively attenuate gamma rays and shield against neutron radiation opens up a wide range of applications. One of the most significant areas is nuclear safety. These composites can be used to create robust shielding structures in nuclear power plants, protecting personnel and the environment from harmful radiation. Their enhanced properties make them ideal for constructing containment vessels, spent fuel storage facilities, and other critical infrastructure components. Beyond nuclear power, these composites find utility in medical facilities. They can be incorporated into the walls, floors, and ceilings of radiology rooms, safeguarding patients and healthcare professionals from scattered radiation during diagnostic imaging and therapeutic procedures. Furthermore, their use extends to sustainable construction practices. By utilizing waste materials, these composites contribute to a circular economy, reducing the reliance on virgin resources and minimizing the environmental impact of construction activities. The future of radiation protection is being shaped by the innovative use of waste. These advanced cement composites, a testament to human ingenuity, offer a beacon of hope for a safer, cleaner, and more sustainable world. Hey there, science fans! Cement is everywhere. Buildings, roads, bridges, you name it, it's probably got cement in it. This wonder material is made from stuff you find in the ground like limestone and clay. We mix it with water, it hardens, and bam, instant structure. But here's the catch, making cement gobbles up tons of energy and spits out a surprising amount of carbon dioxide, a major greenhouse gas. We're talking about 8% of global CO2 emissions. Not cool, cement, not cool. Now, I love a good building as much as the next guy, but we need to find a way to make cement more sustainable. That means using less energy, emitting less CO2, and even figuring out how to use waste materials in the mix. Sounds like a job for science. Luckily, researchers worldwide are on the case. One promising avenue, you guessed it, blending cement with recycled PVC. PVC, or polyvinyl chloride, is another common material found in pipes, flooring, and even those inflatable pool toys. It's durable, versatile, and, get this, recyclable. But here's a fun fact. PVC doesn't break down easily in landfills, So what if we could take this long-lasting plastic and give it a second life as a building material? That's right, we're talking about mixing it with cement. Now you might be thinking, Bill, how do you mix plastic with cement? Great question. Scientists have found clever ways to grind PVC into a fine powder. Then they can add it to the cement mix in different amounts to see how it changes things. But why even bother? Well, adding PVC to cement isn't just about finding a place to dump old plastic. It's about potentially making the cement stronger, lighter, and more resistant to pesky things like water damage. Let's get down to the nitty-gritty. Does adding PVC actually make cement stronger? To find out, scientists put these newfangled cement mixtures through a series of rigorous tests. One of the most important tests is the compressive strength test. Imagine a big, strong machine pushing down on a block of cement with incredible force. Compressive strength tells us how much squeezing the cement can handle before it starts to crumble. We measure this in megapascals, MPa, which is a fancy way of saying units of pressure. The results? Adding a small amount of PVC, like 5% by weight, can actually increase the compressive strength of cement. It's like giving the cement a backbone of super strong plastic fibers. This means we could potentially use less cement overall, saving resources and energy. Now that's what I call a win-win. Section 4, Porosity Puzzle, Tiny Holes, Big Impact. Here's a fun fact. Cement isn't as solid as it looks. It's actually full of tiny holes, kind of like a sponge. We call this porosity. While these tiny voids might seem insignificant, they play a big role in how strong and durable our cement structures are. So, how does PVC affect these miniature air pockets? Well, it turns out that adding PVC to the mix can actually make the cement less porous. That means fewer gaps and cracks for water to seep in and cause damage. Less porosity also means the cement is denser, which can be a good thing for things like foundations and retaining walls where you want to keep water out. It's all about finding the right balance of strength, porosity, and durability for the job. Section 5. Building a greener future, one brick at a time. Adding recycled PVC to cement is like giving those old plastic bottles a superhero cape and a chance to save the world, one building at a time. It's a great example of how we can use science and innovation to tackle environmental challenges and create a more sustainable future. This superpowered cement has some seriously cool potential applications. Think stronger, more durable roads and bridges that last longer and require less maintenance. Imagine buildings that are more resistant to water damage and weathering, reducing the need for repairs and replacements. But we're not done yet. Scientists are still hard at work exploring different types of PVC, optimizing mixing ratios, and developing even more eco-friendly building materials. It's an exciting time to be a cement enthusiast, and I, for one, can't wait to see what amazing innovations the future holds. Stay curious, my friends. Space is vast and wondrous, filled with celestial wonders that spark our imagination, but the cosmos also harbors invisible dangers. Radiation, in its many forms, constantly bombards our planet. Cosmic rays from distant supernovae, solar flares from our own sun. These energetic particles pose a threat to life and technology alike. Here on Earth, we've learned to harness the power of radiation for good in medical imaging and cancer treatments. Yet this power demands respect. Uncontrolled exposure can be harmful, even deadly. That's why we need robust shielding, materials that can absorb and deflect radiation's invisible onslaught. Think of it as cosmic armor, protecting us from the universe's invisible dangers. For decades, concrete has been the go-to material for radiation shielding. It's readily available, cost-effective, and relatively good at absorbing radiation. But concrete has its limitations. It can be bulky and heavy, requiring significant structural support, and its effectiveness varies depending on the type and energy of radiation. That's why scientists are exploring new frontiers in material science, seeking advanced solutions for a safer, more sustainable future. This is where advanced cement composites take center stage. Imagine a material that combines the strength of concrete with enhanced radiation-absorbing properties. That's the promise of advanced cement composites. These materials start with the familiar binder of cement, but incorporate carefully selected additives to enhance their shielding capabilities. Think of it as fine-tuning the recipe, adding ingredients to create a material that's not only strong but also highly effective at blocking radiation. Two such additives, polyvinyl chloride, PVC, and asphaltene, have emerged as promising candidates in this cosmic quest for better shielding. PVC, a common plastic found in everything from pipes to flooring, possesses inherent radiation-attenuating properties. Asphaltene, a complex mixture of organic compounds found in crude oil, exhibits a similar ability to absorb radiation. By incorporating these materials into the cement matrix, researchers aim to create composites that are not only mechanically robust, but also highly effective at shielding against harmful radiation. PVC's ubiquity in our daily lives often overshadows its hidden talent: radiation shielding. This versatile plastic, known for its durability and affordability, possesses a unique atomic structure that makes it adept at absorbing gamma rays, a highly penetrating form of radiation. When gamma rays encounter the chlorine atoms within PVC, they transfer their energy, effectively reducing the radiation's intensity. This makes PVC an attractive additive for enhancing the shielding properties of cement composites. But it's not just about adding PVC to cement, it's about finding the optimal balance. Researchers are meticulously studying how different concentrations of PVC affect the composite's mechanical properties and shielding performance. Too little PVC and the shielding improvement might be negligible. Too much and the composite's strength and workability could be compromised. It's a delicate dance between maximizing radiation absorption without sacrificing the material's structural integrity. Section 4: Asphaltene, tapping into nature's shielding. Asphaltene, a naturally occurring component of crude oil, presents another intriguing avenue for enhancing radiation shielding. This complex mixture of organic molecules, often considered an undesirable byproduct of oil refining, possesses an inherent ability to attenuate radiation, particularly neutrons. Neutrons, electrically neutral particles found in nuclear reactions, can penetrate deeply into materials, making them a significant shielding challenge. Asphaltene's unique molecular structure, rich in carbon and hydrogen atoms, effectively scatters and absorbs neutrons, reducing their energy and preventing them from reaching sensitive areas. Like PVC, incorporating asphaltene into cement composites requires careful consideration of its concentration and distribution within the cement matrix. Too much asphaltene can negatively impact the composite's strength, while too little might not provide the desired shielding effect. Researchers are actively investigating the optimal asphaltene content to achieve a balance between mechanical robustness and effective neutron shielding. Section 5: A tale of two composites, strength and shielding prowess. Now comes the moment of truth. How do PVC-based and asphaltene-based cement composites stack up in terms of both strength and shielding performance? Through rigorous testing and analysis, a fascinating story unfolds. PVC-based composites excel at shielding against gamma rays, demonstrating a significant increase in radiation attenuation compared to conventional concrete. This enhanced shielding arises from the high atomic number of chlorine in PVC, which effectively interacts with and absorbs gamma radiation. The addition of PVC also improves the composite's compressive strength, making it more resistant to cracking and deformation under stress. Asphaltene-based composites, on the other hand, emerge as champions against neutrons. The abundance of hydrogen and carbon atoms in asphaltene effectively scatters and absorbs neutrons, making these composites particularly well-suited for applications involving neutron radiation, such as nuclear reactor shielding. While asphaltene's impact on compressive strength is less pronounced than PVC's, it still contributes to a denser, more robust material compared to plain concrete. Section 6: Applications beyond the beam, safeguarding our world. The development of these advanced cement composites has far-reaching implications, extending far beyond the realm of scientific curiosity. Imagine a world where nuclear waste, a byproduct of our growing energy demands, can be safely stored and contained, minimizing the risk of environmental contamination. Picture hospitals equipped with more effective radiation shielding, protecting patients and medical personnel from unnecessary exposure during diagnostic imaging and cancer treatments. These are just a few examples of how advanced cement composites can revolutionize various industries. Their enhanced radiation shielding properties, coupled with their mechanical strength and durability, make them ideal for a wide range of applications, including nuclear power plants, shielding reactors and containing radioactive waste, medical facilities, protecting patients and staff during radiation therapy and diagnostic imaging, research laboratories, providing safe environments for handling radioactive materials, security checkpoints, enhancing the detection of radioactive materials in luggage and cargo, space exploration shielding spacecraft and astronauts from cosmic radiation. Section 7. The Future of Shielding, a Universe of Possibilities. The journey of advanced cement composites is far from over. As we delve deeper into the intricacies of materials science and radiation interactions, new possibilities emerge. Researchers are exploring novel additives, optimizing mixing ratios, and developing innovative manufacturing techniques to further enhance the performance and versatility of these remarkable materials. Imagine composites that can adapt to different radiation types and intensities, providing customized shielding solutions for specific applications. The future of radiation shielding is bright, driven by the pursuit of knowledge and the unwavering commitment to creating a safer, more sustainable world. As we continue to explore the cosmos and harness the power of radiation for good, advanced cement composites will undoubtedly play a pivotal role in safeguarding our planet and its inhabitants from the invisible dangers of the universe. We live in a world increasingly reliant on powerful technologies. These technologies, while beneficial, often produce an unwelcome byproduct radiation. From medical imaging to nuclear power, radiation is a constant companion. As we venture further into the cosmos and harness the atom's power, our need for effective radiation shielding grows ever more critical. This is where the innovative use of materials like PVC and asphaltene comes into play. These materials, often found in everyday items, hold the potential to revolutionize radiation protection and nuclear waste management. The quest to safeguard ourselves and our environment from harmful radiation is not merely a scientific endeavor, it's a matter of global importance. As we push the boundaries of science and technology, we must also prioritize the development of sustainable and effective shielding materials. Imagine a future where hospitals, research facilities, and even spacecraft are equipped with advanced, eco-friendly radiation barriers. This vision, while ambitious, is within our grasp. Before we delve into the specifics of PVC and asphaltene, we must grasp the fundamental ways radiation interacts with matter. Imagine a beam of radiation invisible to our eyes penetrating a material. This interaction depends on several factors, one of the most crucial being the material's effective atomic number. Think of the effective atomic number as a measure of how densely packed the atoms are within a material. A higher effective atomic number generally translates to better radiation absorption. Lead, for instance, with its dense atomic structure, is a well-known radiation shield. However, the story doesn't end with the effective atomic number. The energy of the incoming radiation, whether it's high-energy gamma rays or lower-energy X-rays, also plays a critical role. Different materials and their atomic arrangements interact differently with varying radiation energies. Understanding these nuances is crucial in developing effective shielding for specific applications. This is where the unique properties of PVC and asphaltene come into play. PVC, or polyvinyl chloride, is a ubiquitous plastic known for its durability and versatility. Asphaltene, a complex mixture of hydrocarbons, is often found in crude oil. While these materials might seem worlds apart, they share a crucial characteristic. When incorporated into cement, they significantly enhance its radiation shielding capabilities. Cement, a ubiquitous construction material, is already a decent radiation absorber due to its composition. However, adding PVC and asphaltene takes its shielding power to the next level. These materials, when dispersed within the cement matrix, increase its effective atomic number, making it more effective at attenuating radiation. The result? A robust, cost-effective, and readily available material that can be used in various radiation shielding applications. Section 4. Enhanced shielding. A closer look at neutrons and gamma rays. Let's delve deeper into how these composite materials combat two of the most penetrating forms of radiation: neutrons and gamma rays. Neutrons, neutral particles found in atomic nuclei, are particularly difficult to stop. They can travel great distances through air and penetrate deeply into materials. This is where the unique properties of PVC and asphaltene modified cement shine. Asphaltene, rich in hydrogen, acts like a neutron sponge. Hydrogen atoms are exceptionally effective at slowing down fast neutrons, making them easier to capture and neutralize. PVC, on the other hand, contributes to the composite's ability to attenuate gamma rays. Remember exposure buildup factors, or EBF? These factors quantify how scattered radiation contributes to the overall dose. PVC helps reduce EBF, minimizing the amount of scattered radiation that can escape the shielding material. The combined effect is a material that provides superior protection against both neutrons and gamma rays. Section 5. Comparing new composites with traditional materials. How do these new composite materials stack up against their traditional counterparts? Lead, the gold standard in radiation shielding, is incredibly effective but comes with its own set of drawbacks. It's heavy, toxic, and expensive. Concrete, while readily available, requires significant thickness to provide adequate shielding, making it impractical for some applications. This is where PVC and asphaltene modified cement offer a compelling alternative. These new composites provide a balance of affordability, effectiveness, and sustainability. They can be easily molded into various shapes and sizes, making them suitable for diverse applications. Moreover, using readily available and often recycled materials makes them an environmentally responsible choice. This makes them particularly appealing for large-scale infrastructure projects where sustainability is paramount. Section 6. A sustainable future: environmental impact and applications. The environmental impact of any new technology is a crucial consideration in the 21st century. Fortunately, PVC and asphaltene modified cement tick several boxes on the sustainability checklist. Utilizing recycled PVC and asphaltene, often considered waste products, reduces the demand for virgin materials and minimizes waste. This circular approach aligns perfectly with a future where resource conservation is paramount. The potential applications of these composite materials are vast and inspiring. Imagine hospitals equipped with lightweight yet effective shielding, reducing exposure for both patients and medical professionals. Picture nuclear power plants with enhanced safety features, minimizing the risk of radiation leaks. Envision spacecraft shielded against cosmic radiation, enabling safer and more extended human exploration of the cosmos. These are just a few glimpses into a future where innovative materials like PVC and asphaltene modified cement play a crucial role in shaping a safer and more sustainable. As we wrap up today's episode on For Science Salah Lotfy channel, we would like to extend our deepest gratitude to the brilliant researchers who made this study possible. Their dedication to science and innovation has led to the development of sustainable materials that enhance nuclear safety. This remarkable research was conducted by Professor Dr. Hosam Saleh, Radioisotope Department, Nuclear Research Center, Egyptian Atomic Energy Authority, Cairo, Egypt. Emeritus Professor Dr. Ibrahim, Bondouk, Physics Department, Faculty of Science, University of Tanta, Egypt. Professor Dr. Elsayed, Salama, Basic Science Department, Faculty of Engineering, the British University in Egypt, Shorouk City, Egypt. Professor Dr. Hosam Mahmoud, Radioisotope Department, Nuclear Research Center, Egyptian Atomic Energy Authority, Cairo, Egypt. Emeritus Professor Dr. Khalid Omar, Physics Department, Faculty of Science, University of Tanta, Egypt. Dr. Hiba Essawi, Basic Science Department, Faculty of Engineering, the British University in Egypt, and School of Science and Engineering, the American University in Cairo, Egypt. We truly appreciate their efforts in advancing nuclear safety and sustainability. And of course, a big thank you to you, our viewers, for joining us on this scientific journey. We'd love to hear your thoughts. What do you think about using waste materials like PVC and asphaltene in radiation shielding? Could this technology play a role in the future of nuclear safety and sustainable construction? Share your opinions in the comments below. If you enjoyed this episode and want to stay updated on the latest scientific breakthroughs, make sure to like this video to support our work. Subscribe to For Science Salah Lotfy channel for more cutting-edge research. Hit the notification bell so you never miss an update. Your support helps us bring more valuable scientific content to a wider audience. Science continues to transform the world, and together, we can explore its wonders. Thank you for watching, and we'll see you in the next episode on For Science Salah Lotfy channel.